So today we are starting our volumes. Volume is the last thing that we're going to be looking at for this entire course. So we're going to be looking at first this week is volumes with cross sections. Then the next type of volume we're going to be looking at is volumes of revolutions, where we spin things around and make volumes. Okay? I hope to kind of go at a little bit slower pace to try to make sure that we kind of understand both conceptually and visually what is happening with these. Because if you can't have a good visual understanding of what's happening, these just don't really make sense. They are difficult problems, but if you have a good visual understanding, then it makes it easier to understand what's going on. So we're going to take it at a slow pace. But this is what we're looking at. Shapes like this, where we have volumes with what we call our cross sections. What do I mean by a cross section? Well, a cross section is, let me go ahead and grab my water bottle over here. So this water bottle is a solid volume, right? Okay, it's a 3D shape. If I was to take some kind of saw and cut down through the volume, that cut that I would make, you'd take it apart and look at it. Like if I was to cut straight down, this would be my shape. What shape do I have? Circle. If I was to cut straight down my water bottle, right? If I was to cut at a diagonal, it would end up being an oval, okay? So that's a cross section. This shape that we get when we cut down is a cross section. Have you guys, any of you played the like ninja slicing games? Where you slice the fruit or whatever? How many of you guys played those? Okay. You're cutting cross sections with those. Without thinking about it, you're doing some calculus. Okay? When you cut through and slice through those fruit, or the one I also remember they had one on the old Wii, the sword game, right? And you'd slice through, it wasn't just fruit, you'd be slicing in like big pencils or TVs or different things like that. Do you remember that? Okay. That slice that you take with your sword through that object, when you take it apart and they show that cut, that is a cross section. Okay? So what we're looking at is volumes that have that cut where the shape is known, okay? So they're going to tell us, hey, your cross-section is a square. So when you cut, you're going to have this square inside. Hey, your cross-section is a rectangle. Your cross-section is a triangle or a semicircle. Those are really the four shapes that we're going to be dealing with. Squares, rectangles, triangles, and semicircles. Today, we're really just going to focus on squares and rectangles, okay? So if you look at this object that we have on the board, on your paper, that orange section that I have is the cross section. So think about you're taking your sword and you're cutting through that object. That shape is your cross section, okay? Now, to help us get a little bit better idea, I have some other visuals for us. Okay, I'm going to start with this. Okay, I built this with GeoGebra to kind of help us have a good visual. So hopefully this works the way I want it to. So right now, this is our normal 2D, right? We're used to this. The red is our x-axis, so the green is the y-axis. Actually, if you look closely, it actually even says that someplace. Maybe it doesn't. Okay, what kind of shape do I have? A parabola. That would just be x squared. Actually, in this case, it is x squared. I think I have that up here someplace. Yeah, the very top one. F of x equals x squared. But we are now in the 3D plane. So what can I do? So I start shifting. We have a third axis. Do you know what that axis is called? The z-axis. But notice, my parabola, is it still in that xy plane? Yes. Okay. the shapes that we are going to be given, or the equations that we are going to be given, are going to be in the xy plane. They're going to tell us, hey, this is the base of your solid. Okay? Now I'm going to do something. I have built in this a polygon, which is it's actually an isosceles triangle, the one that I have. I just need to go for it. Let me actually, I think I can do this. There we go, that works. So let me turn my polygon on. All right, so there's my polygon. Notice, the parabola, again, is the base. What is going up vertically? My triangle. But what creates the base of the triangle? What is that based off of? And I can shift this parabola, or shift this triangle, and what changes on this triangle? The base. And how does it change? According to the parabola. Okay? Now, I want to show you guys a couple things. Let me flip it over here. So, I'm going to turn in on something called trace, if it will let me. Oh, that's right. I need to go back. Let me do something real quick. Let's see if it'll let me do it here. I don't know if it will. Yeah, here we go. I want to open in the app. Okay. So GeoGebra is actually a free software that you can use as well if you're interested in playing around with it. All right, so there is my triangle. I'm going to turn on something called trace. So I'm going to show the trace of this function. I am also going to change I think I have it here. Yes, I'm going to make this a thicker thing here. All right, so what will happen? These volumes, if you think about it, if I was to cut very thin slices of my shape, I would end up with very thin slices of these triangles or squares or whatever I'm dealing with. So then if I was to put all those thin slices together, what would I end up with? A full solid, a full volume. And that's what's going to happen here when I move it, because now I turned on this trace. So every place it's going to trace the shape of that figure. And as I move it, it will create the entire volume shape. You ready? So as I do this, and as I go slowly enough, it creates all these triangles that together will create my entire volume. Okay? So now I can go ahead and turn this around, and what kind of shape has been created? A bunch of triangles, but are they kind of converge at a point here at the vertex of the parabola, right? So they're all triangles, but together they create this curved shape that will form as I do this. This is what we're going to be dealing with, okay? And we're going to be doing the calculus to be able to allow us to find the volume of these shapes. Okay? So kind of give you a visual of what's happening here. So let's go ahead and go back to our notes and get a little bit more into the calculus. Okay? All right, so first thing I want to talk about, we have this formula here. This is how we find the volume of a solid. Regardless of what we do, this is our formula from this point forward. Okay? Volume is the integral from A to B of the area of the cross sections. So if you think about that, let's actually go back to my shape over here. Okay? To get this, actually went away from me, so let me see if I can move my figure. So if I was to take each of these little cross sections, okay, they're all triangles, right? They all have an area. How do we find the area of a triangle?
1/2 base plus 1/2 base times
1/2, so 1/2 of my base. Again, what is my base based off of?
x squared.
The x squared, my parabola, times the height, whatever I designated as my height, and they'll tell you, okay? Okay, so 1/2 base times height. To get my volume, I would need to take each of these little triangle areas and add them together, right? But if I want to get a full volume, I need to have an infinite number of triangles. Infinite number of little triangles that I add together, right? So each of those triangles are my cross sections, and I take each of those infinitely thin slices, each of those infinitely thin triangles here, and I add them all together, and I get a volume. That is what our integral is. If you think back to the Riemann sums, right? What did a Riemann sum do? What was it approximating? Area under curve. We said, okay, I'm going to take each of these little sections, right? And I'm going to add them together. But then that's just an approximation. How do we make that approximation better? Smaller widths and more rectangles, right? So if I make that width smaller, I can make a better approximation, right? As I make those widths small, that's what the integral does. If I go from a to b and say this is f of x, the integral, the definite integral from a to b of f of x, says we are going to be taking infinitely thin rectangles and adding them all together, and that gives us our actual area. Okay? So this is just taking that idea of the Riemann sum and expanding it to our volumes. So in this time, with the Riemann sum, we're taking infinitely thin rectangles, right? With our volume, we are taking infinitely thin little cross-section areas, okay? So we are saying that we are taking infinitely thin, so I would have, hey, here's a cross-section, right? I draw that out, so there's one cross-section. I take another cross-section, and I take that one. I take another cross-section, right? And we just keep on doing that, these infinitely thin cross-sections. Now, if I had this kind of this rectangle here, let's take that cross-section out and say, hey, we have this cross-section like this. How do I find the volume of that shape? What do we do? Length times width times height. Let's say this is my width, this is my length, and that's my height. So altogether, that's going to be width times length times height. But what is length times height? What is that? The area of what? Of that shape. So that is my area of that shape. Okay? Width we call delta x, which actually turns into dx. Okay? So width becomes our delta x or dx. It's that infinitely thin width that we have here. Well, if I take area times that infinitely thin width, and I say, okay, that's going to be the area or the volume of one of my cross sections. Now I'm just going to take and sum up all of those. Well, that's the integral. And that's how we get it. So this a of x, as I say in here, the a of x is the area of the cross section. Now, the formula for a of x is going to change based on the shape of our cross section. But we're going to take that area of that shape, we're going to multiply it by its width, the dx, and that creates the volume of our infinitely thin cross section. We just sum up all of those infinitely thin cross sections, and we get our volume. Okay? That's how we get this. So the a of x dx, that is a volume. It's area times an infinitely thin width. That's volume. And then the integral, we're just summing all of those up. So, you ready to do a problem? All right, let's do it. Let's look at problem 1. All right, so the base of a solid. So this is our xy plane. But what did we see with that last problem I showed you with GeoGebra? That's going to kind of go down, fall down horizontally, and what's going to be coming up? What's that axis coming up? The z-axis. So this parabola is flat on the base, and we're going to have these volumes, this volume coming up. So this is the base of the solid, is the region bounded by a parabola, x squared, and the line 4, g of x equal to 4, y equals 4, right? We see that, the blue line there, as shown in the figure below. So we're going to determine the volume of the region if each cross-section perpendicular to the x-axis is a square. That is important. This phrase right here, perpendicular to the x-axis, is important. That perpendicular to the x-axis is going to tell us, are we in terms of x or are we in terms of y? If it is perpendicular to the x-axis, what do you think we are in terms of? The x. Okay? If it is perpendicular to the x-axis, well then we are in terms of x. Makes it easy on us. If you see perpendicular to the x-axis, everything should be in terms of x. So this is in terms of x. Okay? So let's go ahead and just kind of visualize what's going on here. And I'll actually pull up, I have another applet in GeoGebra that will actually show this entire thing for us. Okay, it says our shape is a square. That's important. So let's see if we can visualize this a little bit. So let's change our perspective. So let's say, hey, here's my x-axis kind of coming out like that as my y-axis. And then coming up is my z-axis. My parabola is coming down like this, right? That's my parabola. At y equals 4, so 1, 2, 3, 4, is that line coming through like that. And then what is the cross-section shape that's coming up? A square. So that means, and it is perpendicular to the x-axis. Now, before I had my shape, the base going like that, but what would that be perpendicular to? The y-axis. So no longer am I like that. Mine is going to be coming down perpendicular to the x-axis. So it's going to be coming down like that. Now it is going to be from between the curves, so that's my base, and then I would need to come up as a square, and that would be my square, okay? So that's one cross-section. I could do another cross-section here, going like that, okay? And so forth, okay? So that's kind of visually what's going on. Now, obviously that's not the best drawing in the world, so let's let GeoGebra do the work for us. Okay? So I have this link here. It's this one that I want. All right, so this is already here for us. Let me see. I think I can. Yes, I can make this full screen. All right. So this is a very nice program. Somebody a lot smarter than I created this. So in here we have our two bounds. So y sub 1 is our first function. That's x squared. Does that match with what we're looking at? Okay. And then our other bound is y equals 4. Does that match? Okay. We can change those if I need to. It says cross sections are perpendicular to the, we want to the x-axis, so that's checked off. Okay. We have our lower bound and upper bound. So what was the bound that they tell us? Did they give us any bounds? They did not, so it's going to be where they intersect. Okay, so if we look at this, where do these figures intersect? -2 to +2. So those are our bounds, and those are in there already, so that's good to go. But what is our cross-section shape? Right now they have it on triangle. What is our cross-section shape? So let me check. Square. So that changes it. And now I can draw the shape. And it does it for me. So this is what our shape is going to look like. We can spin it around and look at it.
Wow.
Does that? If I put it on its side, do we see all those square cross sections? Yeah. But all together, they create this like curved shape, right? It's pretty cool, huh? Now, they're telling us this, what's nice about this applet, my answer's right down there, volume. But we need to do the calculus. So, let's go ahead and talk about how we would do this. All right. On the side, let's go ahead and just remind ourselves, what was that integral that I told you? The volume is equal to what?
The integral from a to b of a of x dx.
So we need to figure out what is that a of x. To help us, let's think about our cross-section. Okay, so let's look at our cross-section. So I would recommend always doing this, cross-section. What was our cross-section shape again? A square. So we're looking at a square. Well, let's draw a square. So this is our cross-section shape. And we want to know what is the area of that square. Okay? Now that should be fairly easy to think, but I want you guys to notice this. This cross-section is going to be drawn just as I did 3D. I can draw out, and I would recommend doing this, on your actual graph. We are perpendicular to the x-axis, so this is going to be the base of my cross-section, something like that, okay? That is the base of my cross-section. And so I'm going to highlight that on my square with that same color. That is the base. Now, let's just label that as B, base. How do I find the area of a square? Length times width, but what do we know about the length and the width? They're equal, right? So then what would be my area? Just B squared. But what is important is we need to determine what is my B. So let's go back to my graph. What is the top bound of my graph? The equation 4. What is my lower bound of that base? X squared. So my base, what do you think, how would I express the base? 4 minus x squared. That's the base. Because I do the top bound of 4 minus the lower bound of x squared. That is my equation for the base. 4 minus x squared. Okay? Sometimes it helps me to visualize. I would say, hey, I have this larger length of blue. Yeah, blue, this larger length of blue. What's the length of my blue line that I just drew? 4. And then I have this smaller length down here of red. So to get my pink length, I'm going to do my larger length of blue minus the smaller length of x squared. Okay, so 4 minus x squared gives me my pink. And it doesn't matter where I'm at. I can go over to here and say, hey, here's the base of my square. But to get that pink length, again, it is the 4 minus the x squared. It is exactly the top minus bottom thing again. Okay? Top minus the bottom. And that gives us that base. So, how can I express my area function then? My area function is b squared. So, what do I write? There we go. Now, how do I do my volume then? I just plug everything in. So, what are my bounds of my volume? From where to where? -2 to 2. So our integral is going to go from -2 to 2. My area expression is 4 minus x squared squared. And then I tack on my dx, the width of that infinitely small slice. And that's how I find my volume. So let's go ahead and pull out our calculators and plug that in.
Wait, will we probably not get a calculator on this question? Like, if it was in the
This could be done with by hand. I could box or foil that and do it by hand, but let's just quickly throw it in our calculator and see what we get. And see if it matches up with what GeoGebra is saying. All right, what are we getting as our volume? Which should be the same thing, right? All right, so that's what I'm getting. Does that check in with what GeoGebra said? Let's go back and check. Is that what they were saying? Yeah. There we go. Pretty cool. All right. Let's go ahead and look at our next problem then. Before I do, any questions on this? Okay. So let's go ahead and think about the next one. So B, we have the same graph, but what is our cross section now? What does it tell us? It is perpendicular to the x, and our cross section is
a rectangle with height plus 1 base.
okay. So again, let's think about our cross section. It is the same shape as what we have above. But this time, our cross-section is a rectangle where, again, let's say this is our base, but what is our height? What does it tell us? Our height is twice the length of, so how would I express the height? 2b. How would I express that area then? B times 2b. B times 2b. What is that? Not 3b. That'd be adding, multiplying. 2b squared. 2b squared or not to be squared? Anyways. All right. How do we express our base in terms of our problem? Well, it's the same as the last problem, isn't it? So then it should still be the same. 4 minus x squared. Right? So then our area function it should be 2 times 4 minus x squared squared. Well, now that I know what the area formula is, I can build my integral. So volume is going to be the integral from -2 to 2. And then that's a of x dx. So 2, 4 minus x squared, squared dx. All right, let's calculate that. So I should be able to go back to my previous one and just multiply that by 2. Right? So we should get volume equal to 68.267. Okay. Do you want to visually see this? And check to make sure that we did it correctly. So we're going to have to adjust a couple things. We still have x squared, we still have 4, our bounds are still negative 2 and 2. But this time I'm doing a rectangle, and I have to change what my height is. What was my height? 2 times b, but what was my b? 4 minus x squared, right? Okay, so let's go ahead and see what it does. Oh, it's a little big, so I'm going to go ahead and pause this. I'm going to zoom out so we can actually get the whole shape. Let's do that again. So it's a lot larger, right? Why is it larger? The height is doubled, right, than the square. Is that what we got for our volume? 68.27? Yeah, let's just move this around so we can kind of visualize what's going on. So kind of same shape as the other one, but all our cross sections are rectangles twice as tall. All right? Does that make sense, what we're doing? A little bit? Okay. Let's go ahead and look at another one then. Let's see. Well, this is a fun one. All right. What I want you to do, we don't have a ton of time. We have about 4 minutes. I want you to try this one on your own. Okay. Think about what we're doing. We have a part A that's a square, again, still perpendicular to the x-axis. Part B is a rectangle, again, perpendicular to the x-axis. All right? So the process should be very similar. Okay? All right? So, go ahead and try. Yes? No. We don't have to do that at all because we're doing instead is the area of the cross section. So you are more concerned with what is your cross section and how would you find the area of that square. Okay? And remember, we get that by doing that little cross section here. How do we determine that is our base? Okay? Okay, at least try to see if you can get A done. Now, we don't have a ton of time, but try. See what you can do. Not a ton of time, so let's check your part A. So I have everything set up here. I have my upper bound as the linear function. Lower bound as the quadratic, going from 0 to 2. I have it on a square. So let's go ahead and see what our shape would look like. So it's building out that shape for us. And they're saying our volume is 9.75. How did you guys do? And that is our shape. Pretty cool. All right, do you have your homework? I will do a couple more of these, send them out to you as some example videos so you can watch and see. But have a wonderful day, everybody. We'll talk and see each other later.
Me too. Me too. It hurts.